Hello friends, in the last lecture we were talking about instruction format and think we discussed about this slide. Like we discussed about uh, the instruction format, the integer format, the registers and how opcodes are given. Let's take one example and let's see how your computer works with a simple program. Okay, see, this is the contents of your memory, and these are your CPU registers. And let's see what happens when you get some kind of instruction. See, this is your first step. As the contents of PCR 300, the CPU will fetch the contents of location 300 and copy those contents into, as it is instruction, it will be copied into instruction register. See, the contents are 1940. Now, as we have discussed the instruction format, see, first 4 bits are your opcode and remaining bits are your address. So 940 is your address and this is your opcode. So 1 means 0001 and 0001 means load AC from memory. So what happens is the contents of location 940 will be copied into accumulator. See, in next step, these contents are copied into your accumulator, and as the instruction from location 300 is fetched, the contents of PC are incremented. So now the contents of PC are 301, and now next instruction will be fetched. Three, uh, at 301 location, there is this instruction 5941. So this instruction will be copied into instruction register. Okay. So see, first instruction is executed. Copy contents of memory into load AC from memory. This instruction is executed here. Now the second instruction is fetched and it is copied into your instruction register. Again, see, this is your opcode and this is your address. So 5 will be represented as 1001. Okay. So 1001 means uh, actually this is the opcode for addition. So that's why in next step addition is done. Add contents of this location into accumulator. That is the meaning of this opcode. 1001 means add contents of this location specified in the instruction in your contents of accumulator. Okay, so what happens here is contents of 941 location, that is 2, will be fetched and it will be added to contents of your accumulator. And in next step, the contents of accumulator will be, so this there is after addition 3 plus 2, 5. So your contents of accumulator is now 5. And again see, as second instruction is fetched, the contents of PC are again incremented. Now the content is 302. Now let's see what is there at the location 302. So at location 302, this instruction is there, 2941. So again this is fetched and copied into your instruction register 2941. So 2 is your opcode now. So that is 0010. 0010 means store contents of accumulator 2 memory. So whatever this instruction means, copy the contents of accumulator to this location 941. Okay. So now in the next step, the contents of accumulator are copied to this 941 location. I hope you have understood how the instruction works and how the opcodes are represented, opcodes and locations. And for your better understanding, these numbers are represented in a decimal format, but actually when these numbers are stored in your computer, they are in binary format, in bitwise format. Okay, now let's discuss about instruction cycle state diagram. In the last lecture, we have discussed about instruction cycle, and I think there are only 3 phases, but this is a detailed instruction cycle. See, it starts from here, instruction address calculation. And I hope you remember from our last slide that instruction address is stored in your program counter register, PC register. So from there, you have to calculate the instruction address. Then that from that location, the instruction will be fetched. Then next step is to decode the operation which is indicated in your instruction. After that, next step is operand address calculation. So from your instruction, you will get the address for your operands. So sometimes it is directly given, but sometimes you might have to calculate the address of your operand from where you have to fetch the operand. Then the operand is fetched from that location. If there are multiple operands, this will continue unless all the operands are fetched into your CPU registers. Then next step is the operations will be done, data operations will be done. Then after that, where where do you want to store your result? That address calculation is done in the next step, and this process continues until all the results are stored in your specified location. See, from here, if for this operation you need some other operands, then you have to come to this step, return for string or vector data. And after the result of your instruction is stored, you can come back to our first step, that is calculation of the address calculation of next instruction. Okay, so this is the instruction cycle state diagram. So if any question is asked about instruction cycle state diagram, you have to draw this diagram and not the first one with only 3 phases. Okay, next, our next point is interrupts. Interrupts are actually provided primarily as a way to improve processing efficiency. I hope you understand the concept of interrupts. Interrupt means when something is going on uh, that in case of our computer, if program execution is going on, some interrupts may occur. Like your computer uh, can shut down without any reason, or there is no power supply can be cut and your computer shuts down. So something like that. This is kind of this is one of the type of interrupt. So whatever you are doing, it is interrupted. Okay. There are many other types of interrupts. We'll discuss those in our next slides. See, there are these types of interrupts: program interrupts, timer interrupts, I/O interrupts, and hardware failure. So program interrupts means when there is some kind of unusual condition, something like arithmetic overflow or division by zero, attempt to execute an illegal machine instruction, then that kind of there will be interrupt generated. Your program execution will be interrupted, and that kind of interrupt is called as program interrupt. Next type is timer interrupt. So this interrupt is generated by a timer within the processor. So when you think about your computer, it is performing some functions on a regular basis, on a scheduled basis. So this happens by using the timer within the processor. So if you have scheduled some operation for that for a particular time, even if other program is being executed at the same time, that program will be interrupted. The scheduled process will be done first, and then the computer will start working on the current program execution. So this is called as timer interrupt. Next point is I/O interrupts. These are generated by I/O controller to signal normal completion of an operation or to signal a variety of error conditions. See, when we are talking about I/O, I/O means your input-output devices. So it can be if there is some kind of error in your mouse, or there is some kind of error in your keyboard, or in case of output devices, if your printer is switched off, there will be interrupt generated. Or sometimes what happens is the speed of your I/O devices is really uh, really less as compared to your processor. So what happens is sometimes processor assigns some task to your input devices or output devices, and after they are done with that task, those, those devices, uh, those devices which are controlled by your I/O controller, after that task is done, the I/O controller will signal your processor that this task is completed, and that particular device is ready to perform another operation. So these are called as I/O interrupts. Next type of interrupt is hardware failure. Uh, so as I already told you, these generated by a failure such as power failure or memory parity error, or if there is some problem with your computer hardware, your computer can fail fail to execute the current program. So these are the different kinds of interrupts. Now let's talk about what is I/O program. I/O program has three code segments which do not involve I/O. It has three sections: a sequence of instructions labeled 4 to prepare for the actual I/O operation, the actual I/O command. Once this command is issued, the program must wait for the I/O device to perform the requested function. A sequence of instructions labeled 5 to complete the operation. So these sections doesn't actually involve any input device or output device, but uh, they are just in these sections. These instructions are there to prepare your input output device. Now let's talk about how the flow occurs with the help of this diagram. See, without interrupts, how your computer works. There is your user program. See, this is working. Then there is IO program. At this point, we have requested for some kind of uh, task. You have assigned some kind of task here. Here, input output devices. Then the control will go to your IO module. Then that those instructions will be executed, which are related to your IO. Then the control will come back after completion of this sequence of instruction. Your control will come back to your actual user program. Then it will continue executing that program. Again, when there is an IO instruction, the control will be passed again to your IO module. And all this time, your processor is idle. For this time, when your IO devices are working, your processor is idle. It is not doing anything. And after completion of this, the program execution resumes. So here we are actually wasting a lot of time for your processor. As your processor is very much faster, see in all this time, it can process another instructions, or it can execute different instructions which are not related to this result. Okay, so that's why interrupts are introduced. See, in this diagram, you can see how interrupts can improve the execution and performance of your processor. See, in this case, see here an IO instruction is there. Okay, so there is an interrupt. The control will be passed to IO module, and see here in this case actually the program continues to execute. With different uh, different instructions which are not related to this IO command. Okay. So this is the diagram for short IO wait, and this is the diagram for long IO wait. See, as I already told you, with interrupts, the processor can be engaged in executing other instructions while an IO operation is in progress. When the external device becomes ready to be serviced, the IO module for that external device sends an interrupt signal to the processor. Then the processor responds by suspending operation of the current program. Now, for processing these interrupts, there are again different approaches. First approach is to disable interrupts while an interrupt is being processed. And second approach is define priorities for interrupts and to allow an interrupt of high priority to cause a lower priority interrupt handler to be itself interrupt. Okay. See this is the instruction cycle state diagram. This is just, we have just added interrupts here. So after execution of every instruction, processor will check if there is an interrupt. If an interrupt is there, it will go to that interrupt will be handled first, or it will be assigned to interrupt handler, and then the control comes back to these phases. No. As I already told you, there are two approaches. First approach is sequential interrupt processing. So, see, there are two interrupts, interrupt X and interrupt Y. So, whichever interrupt occurs first, that interrupt will be handled first. And after completion of handling of this interrupt, then only the be control will go to handling the next interrupt. So that's why this is called as sequential interrupt processing. Now, next type is nested interrupt processing. See, here again, two interrupts, interrupt X and interrupt Y, have occurred at the same time. Not exactly at the same time, but uh, while processing first interrupt X, the second interrupt has occurred. But as this interrupt is of higher priority, this is suspended here. First, this interrupt is processed, and then the control will come back to handling the first interrupt. It will complete the handling of first interrupt and again come back to your user program. This is called as nested interrupt processing. And this interrupt handler will be suspended only if this interrupt is of higher priority. Uh, this is uh, this is just an example. See, your user program is being executed here. At that time, t is equal to 0. Now, first interrupt occurs at t is equal to 10. Okay, this is printer interrupt service routine. So this interrupt is from a printer. This is being executed, and while this is being executed, we have got another interrupt at t is equal to 15. As this communication interrupt is has more priority than your printer, this routine will be first executed. Then the control will come back to processing your printer interrupt. Again, at t is equal to 25, another interrupt has occurred, disk interrupt. So again, this has higher priority than your printer interrupt. That's why this is executed first. This interrupt is handled first, and then the control will come back to your printer interrupt service routine. And after completion of this printer interrupt service routine, the control will go back to your user program. We will stop here for today. Thank you.